A guide to model stacking in practice. Definition: as a machine learning learner who have learned a lot of taking part in the competition, especially from Kajal, the writer is saying that the setting in the Kajal is good. Let's go to the introduction. Stacking, also called meta ensembling, is a model ensembling technique used to combine information from multiple predictive models to generate a new model. Oftentimes, the stacked model, also called second level model, will outperform each of the individual models due its smoothing nature and ability to highlight each base model where it performs best and discredit each base model where it performs poorly. For this reason, stacking is most effective when the base models are significantly different. Here are the example and guide on how stacking is most often implemented in practice. Here uh, for this article, I've gone through the related code and datasets in the machine learning, where it's about four persons with two datasets, one for training and one for test CSV, and with that, uh, there are two. Let me showcase the datasets for it first. I'm opening up the CSV file where we can see the structure of the data set. As you can see, we have the computer, four of them, and with the x coordinate and y coordinate for darts training, obviously. So here there's 187 dart at board. For 150 of those, we get to see who threw each dart and where it landed. For the first, we'll get to see where the dart landed. The task is to guess who threw each of the unlabeled darts based on the landing spot. Competitors, we have four of them: Bob, Kate, Mark, and Sue. And we have a graph here showing of the training darts and the test darts with the black dots. On the base model one, k-nearest neighbors is used. Let's make a sad attempt at solving which classification problem using a k-near neighbors model. In order to select the best value of k, will use 5-fold cross validation combined with the grid source. Now one, the partition the training data into 5 equal size folds. Call this test folds for 1 to 10 for k value. For each test fold 1, combine the other 4 folds to be used as a training fold 2. Fit a k nearest neighbors model on the training fold using the current value of k, setting the 3 here for the k neighbor. Make prediction on the test fold and measure the resulting accuracy rate of the prediction. 4. Calculate the average accuracy rate from the 5 test fold prediction. Keep the k value with the best average CV accuracy rate. With our fixed data, we find k with the value of 1 to have the best CV accuracy rate of 67%. Using k value 1, we now train a model on the entire training dataset and make prediction on the test datasets. Ultimately, this will give us about 7% classification accuracy, which is more than 67% accuracy. Base model 2. will be is used using support vector machine, where the hybrid patterns to tune type is used in number 1 YAL2 regularized YAL2 loss support vector classification, number 2 YAL2 regularized YAL2 loss support vector classification, which is primal, and same type with the dual, and number 4 support vector classification by Kramer and Singer, number 5 YAL1 regularized YAL2 loss support vector classification. Cost: inverse of the regularization constant. The grid of parameter combinations will test is the Cartesian product of the 5 listed SVM types, which cost values of 0.01, 0.1, 1, 10, 100, 1000, 2000, which will give 1 cost 0.01, 0.01 for 1, 1 for 1, 5 type 5 for 100 cost, type 5 for 1000 cost, type 5 for 2000. Using the same CB plus grid search approach used for k-nearest neighbors models, here the finding shows the best hybrid parameters to be type equals to 4 with cost 1000. Again, these parameters to be used to train a model on the full training dataset and making prediction on the test dataset. This will give us about 61% CB classification accuracy and 78% classification accuracy on the test data. Now, stacking, meta ensembling. Let's take a look at the regions of the board each model would classify as Bob, Sue, Mark, or Kate. We have two as showcased above with the KNN class regions and the SVM class regions. We have different colors for 4 different participants: Bob for pink, Kate for green, blue for Mark, and purple for Sue. And we can see where are the blues are in the inside more, which is of Mark, and the pinks are on the sidelines, which is of Bob, and the greens are also in the inside, which is of Kate, and the purple is also somewhat in the middle, but the numbers of Sue marks are reasonably very small in the center, but on the outside, as you can see, the purples are way outside than the inside. And in the SVM class regions, we can also see the same scenario here with the different color for the 4 different competitors, where the Mark with the blue dots are in the middle the most, with the Bob pink on the outside, pink at the outside the most, and the Sue also on the outside the most, and the Mark with the green is distributed inside and outside. Let's see what we see in the two different graphs comparing KNN and SVM. The KNN model does a good job at classifying Bob's throw and Sue's throw, but does poorly at separating Kate's throw and Mark's throw. As we can see in the KNN class regions here in the graph, the opposite appears to be true for the SVM model, where it's tagged model. So we can see that combining these two models with stacking will probably be very fruitful. There are few schools of thought on how to actually implement stacking. Here is the favorite applied to our examples. Partition the training data into the 5 test folds. What is done with the fold ID, x coordinate, y coordinate, distance from center, and competitor, which we have 4. 2. Create data set called train meta and test meta. Creating data set called train meta with the same row IDs and fold IDs as the training data set with empty columns YAM1 and YAM2. Similarly, create the data set test meta with the same row IDs as the test data set and empty columns YAM1 and YAM2. Train meta with the fold ID, column fold ID, column x coordinate, y coordinate, distance from center, but we have YAM1 and YAM2 with the blank values, and the last column with the competitors. Now with the test meta, we have x coordinate, y coordinate, distance from center, YAM1 blank, YAM2 blank, and the column competitor, but we do not have the fold ID. Number 3, for each test fold 1 till fold 5, combine the other 4 folds to be used as a training fold. Train fold 1 with the fold ID at the column, second column is x coordinate, y coordinate, distance from center, and competitor. For each base model, k nearest with the k equals to 1, support vector machine type 4, cost equals 1000, which is the best. Pick the base model of the training fold and make predictions on the test fold. Store this prediction in train meta to be used as features for the stacking model. Training meta with YAM1 and YAM2 filled in for fold 1. We have fold ID as the column, x coordinate, y coordinate, distance from center, YAM1, YAM2, and competitor. But as you can see, now we have the values in the YAM1 and YAM2. They are not null as before. Now 4, fit each base model to the full training dataset and make predictions on the test dataset. Store these predictions inside test meta. Now we have x coordinate, y coordinate, distance from center, YAM1, YAM2, competitor. As we can see here, YAM1 and YAM2 are fully packed, and we have no fold ID. Number 5, fit a new model such as the stacking model to train meta, train underscore meta using YAM1 and YAM2 as features. Optionally include other features from the original training datasets or engineered features. Logistic regression from Lebanon R package with the type equals to 6, where the cost is 100, fit to train meta. Use the stacked model layers to make final prediction on test meta. Test underscore meta with the stacking model prediction table can be shown here with the x coordinate, y coordinate, distance from center, YAM1, YAM2, and a new column which is for the prediction, and at the end we have the competitor column. As we can see from the table, the main point to take home is that we are using the prediction of the base model as features, that is meta features, for the stacked model. So the stacked model is able to discount where each model performs well and where each model performs poorly. It's also important to note that the meta features in row I of train underscore meta are not dependent on the target value in row I, because they were produced using information that excluded the target underscore I in the base model's fitting procedures. Alternatively, we could make prediction on the test dataset using each base model immediately after it gets fitted to its test fold. In our case, this would generate test set prediction for 5 k-nearest neighbors models and 5 SMB models. Then we would average the predictions per model to generate our YAM1 and YAM2 meta features. One benefit to this is that it's less time consuming than the first approach. That is, since we don't have to retain each model on the full training datasets. It also helps that our trained meta-features and test meta-features should follow a similar distribution. However, the test metas YAM1 and YAM2 are likely more accurate in the first approach, since each base model was trained on the full training dataset, that is as opposed to 80% of the training dataset, 5 times in the second approach, which is 5 times in the second approach. A stack model hyperparameter tuning. So how do we tune the hyperparameter of the stacked model? Regarding the base model, we can tune their hyperparameter using cross validations plus grid sort, combining two scenarios. Just like we did earlier, it doesn't really matter that what folds we use, but it's usually convenient to use the same folds that we use for stacking. Tuning the hyperparameter of the stack model is where things get interested. In practice, most people, including simply use cross validation plus grid search using the same exact CB folds used to generate the meta-features. There's a subtle flaw to this approach, and let's see, can we spot it? Indeed, there is a small bit of data leakage in our stacking CB procedure. Consider the first round of the cross validation for the stacked model. We feed a model it has to fold 2, fold 3, fold 4, and fold 5. Make prediction on fold 1 and evaluate the performance, but the meta feature in fold 2, fold 3, fold 4, and fold 5 are dependent on the target values in fold 1. So the target values we are trying to predict are themselves embedded in the features we are using to fit our model. This is leakage, and in theory, yes, could deduct information about the target values from the meta features in a way that would cause it to overfit the training data and not generalize well to out of back samples. However, we have to work hard to conjure up an example where this leakage is significant enough to cause the stack model to overfit. In practice, everyone ignores this theoretical role, and frankly, I think most people are unaware that it even exists. That's the main reason. Now we'll be talking about stacking model selection and features. How to know that model to choose as the stacker, and what features to include with the meta features. This is more of an art than a science. The best bet is to try different things and familiarize yourself with what works and what doesn't. And the question is, what other features should be included in for the stacking model in addition to the meta features. Again, this is somewhat of an art. Looking at our examples, it's pretty evident that distance from center plays a part in determining which model will perform well. The Cannon appears to do better at classifying darts thrown near the center, and the Astro model does better at classifying darts thrown away from the center. Let's take a shot at stacking models using logistic regression. We'll use the base model prediction are meta features and distance from center as an additional feature. Sure enough, the stacked model performs better than both of the base models, 75% CB accuracy and 86% test accuracy. Now let's take a look at its classification reasons or overlaying the training data just like we did with the base model. The takeaway here is that the logistic regression stacked model captures the best aspect of each base model, which is why it performs better than either base model in isolation. Stacking in practice. To wrap it up, we'll talk about when and why the stacking in the why you use stacking in the real world. Mostly the use of stacking in machine learning competitions on Kaggle in general. Stacking produces small gains with a lot of added complexity. Not worth it for most businesses, but stacking is almost always fruitful, so it's almost always used in top Kaggle solutions. In fact, stacking is really effective in Kaggle when you have a team of people trying to collaborate in a model. A single set of folds is agreed upon, and then every team members build their own models using those folds. Then each models can be combined using a single stacking script. This is great because it prevents team members from stepping on each other's toes, awkwardly trying to stitch their ideas into the same code base. Which basically means is in stacking there are different models, so it's for um, best while doing the group, because uh, each group members can select their each models and do it by themselves, and then at the end combining the results and showcasing which is the best effective models. One last bit, though, suppose we have dataset with user and product pairs, and we want to predict the probability that a user will purchase a given product if he or she is presented and add with that product. And effective features might be something like using the training data, what portion of the product advertised to a user did he actually purchase in the past. So for the sample user 1 with the product A, in the training data we want to track on a feature like user purchase percentage, but we have to be careful not to introduce leakage into the data. Now we do the following. Number 1, split the training data into folds with different folds: fold 1, fold 2, fold 4, fold up to fold 5. Number 2, for each test fold. Number 3, identify the unique set of users in test fold. Number 4, use the remaining fold to calculate user purchase percent of advertised products each user purchase. Number 5, map user purchase percentage back to the training data with the fold ID and user ID. The fold ID from number 1 and the user ID from number 3. Now we can use user purchase percentage as a feature of our gradient boosting model, or whichever model we can choose or want. Effectively, what we have just done is build a prediction model that predicts user underscore I, that is user's ID, will purchase, which user will purchase which product with probability based on the percent of advertised product we purchased in the past, and use those predictions as meta features for our real model. This is subtle but valid and effective from stacking, one which I often do implement in practice and on Kaggle. So therefore, stacking is very, very useful and best be done in the group. And the benefit of stacking is, while a big group, if using stacking, can have a really big and good prediction at the end, rather than just one model done in any other scenario like we did here, we saw here in CAN and neighbors and SPM model. Combining the two, we can see the differentiate in the prediction for the CAN and neighbors and the SVM model. In one, there is the prediction is good, which is far from the center, and one is good in the center of where the dart is thrown.